Hi, it's Dr. Harris, back with the third video in our discussion of Chapter 6 on statistical inference for categorical data in our Math 111 statistics class. In the previous two videos, we've looked at uh, confidence intervals and hypothesis tests for a single proportion and for the difference between two proportions. Here, the only thing that in common with what we did previously is that we are still going to be working with categorical data, but we're going to be looking at it in a completely different type of hypothesis test in this chapter. It's going to be looking at testing for independence in two-way tables. And so let's get it rolling. See what that's all about. Okay, so in our most recent video slash slideshow, uh, we looked at the question of uh, do males and females at Georgetown College respond differently in terms of whether their preference for sitting in the middle of the classroom. And that brings to mind maybe something that we looked at, I think, all the way back in chapter 1, where we looked at seating preferences for students at UC Davis. And so let's take a look at that. We're not going to look just at the middle of the classroom, but we're going to look more broadly. Does there seem to be some sort of association between gender and seat preference among students at UC Davis based on the survey data that we have collected? Back in chapter 1, it looked like initially that maybe women preferred the front more than men did, and men preferred the back more than women did. So let's see if this new type of hypothesis test uh, indicates that we should believe that that might be the case. And so what we're going to do is we're going to look at the result of our friend X tabs with two variables. Remember, we put the tilde followed by the explanatory variable plus the response variable. And if we're not worried about percentages right now, just raw counts, we would get the output that you see at the top of this slide. And what I've done is I've enhanced it by finding both the row totals and the column totals, but I've also switched the order in which the variables are reported in the columns. And I've made it the more natural front, middle, back arrangement. So we're going to be using this table at the bottom half for our work. And it's an important thing, even though XTabs doesn't give us row totals and column totals, it's important for us to be able to compute those and add them to our table. All right, so we want to be thinking then, how am I going to check to see for a relationship? What's going to be my standard for deciding whether there's a relationship or not? And the basic idea actually involves looking at least at first, it feels like we're going to look at row percentages, and we're going to do that for this table. But in the end, we'll be able to do computations just based on the raw counts. But what I want to try to get us to see by looking at row percentages, what we might be looking for in a relationship. And so if we apply row perk to the output of X tabs, we get the row percentages for the women and the men. And again, we see roughly 16% of the women said they prefer the back, about 27.5% prefer the front, well over half prefer the middle, and we have analogous responses for the men. But what I want to do is not only compute those row percentages, but I want to look at the row percentages for the totals, and I can add that in to my data table as well. And so here again, I've rearranged things front, middle, back. And what I've done is I've added in the row percentage for the totals row. And it's natural to ask how I did that. Let me go back a couple of slides. What I did was to convert this to percentages is I took the 41 divided by 171. That's going to give me the percentage of total respondents who prefer the front. 93 divided by 171 will give me the percentage for the middle, and 37 divided by 171 will give me the percentage for the back. And that's what I've done to get these three numbers down here. And so overall, 24% of respondents said front, almost 54.5% said middle, and about 21.5% said back. Okay, so the idea then is if there's no association, we would expect the individual row percentages for each of the uh, gender responses to roughly match the totals row of row percentages breakdown. And so we would expect that uh, both rows should look kind of like 24, 54 and a half, 21 and a half. We got 27 and a half, 56 and a half, 16 for the women, 19 and a half, 52, 28 and a half for the men. So the question is, are those percentage profiles close enough to the total percentage profile for the whole group? So that's what we're really getting at is there if if there's some sort of relationship, if women truly do prefer the front more than men and men prefer the back more than women, then we're asking, are these percentage profiles different enough from the averages, the overall uh, uh, percentages for the total group? And so the way we're going to do this is we're going to compute what we would expect to see for table entries if each row's percentage profile matched the totals row percentage profile. And the way we do that is by computing for each entry in our table this number, row total times column total divided by overall total. So if we go for females who prefer to sit in the front of the room, there are 94 uh, uh, women overall, right? We go back to the table. There were 94 women overall. 41 people overall said the front. And so the expected number for the women who was in the front turns out to be 41 times 94 divided by 171. And let's go see why we should think that's the case. So the women, total number of women divided by times the total number of people who first in the front divided by the total number of people overall. And that gives us about 24, 22 and a half. So why does this make sense? So let's try to think about it this way. Let's look at the 41 over 171. That's the fraction of individuals who prefer to sit in the front. That was 24%. And so if there are 94 females overall, if the women's row matched exactly the totals row in terms of percentages, then 24% of the 94 women would prefer to sit in the front. And that's where we get this 22 and a half. So if we think about column total over overall total, that's my row percentage for the totals row. And then if I just multiply it by the row total, that will give me what I expect to see for each individual gender in terms of expected number to give that response. So again, 24% overall said front. I've got 94 women. Therefore, my expected total would be 24% of the 94 women. That's where the 22 and a half comes from. I'm going to let you verify all these other expected values, but in each case, we're doing row total times column total divided by overall total. And so these are going to be the expected values for each response. For example, I would expect 51.1 females to say middle of the room and 20.3 females to say back of the room. Notice that these three numbers are going to add up to 94. So I'll let you stop this video if you need to, go ahead and try to verify that these are indeed the numbers that you would get if you follow that formula for each cell in the body of my table. So here's what I've got. At the bottom, I've got the table with the actual counts. In the top, I've got the table with the expected counts. Okay, so the first step in this process, if we're going to do this by hand, is to compute the expected totals. Okay, so we'll flip back to this in just a second, but as I point out, what it appears is that we do indeed see that more women than expected replied front, and more men than expected replied back. So there were 26 responded front for the women, as opposed to the expected 22 and a half. there were 22 men who said back as opposed to the 16 and 2/3 that was predicted by the expected value. And so the question becomes then, are the expected values sufficiently different, or should I say, are the actual values sufficiently different from the expected values that I think that there's really something non-random about this going on? Or is it possible that a table like this could have simply happened by random chance if there really was no relationship between gender and seat preference? And so there are a couple things then. We want to actually state hypotheses, and then we want to figure out what statistic, what number am I going to calculate that will measure the difference between the expected and the observed values. So our hypotheses, our null hypothesis is going to be that there is no relationship, that sex and seat are independent for students at UC Davis, whereas our alternative hypothesis is, oh yeah, there is a relationship, that the two variables are not independent. So no relationship would mean that the variables are independent of each other. Some sort of association, we're not specifying what kind of association there is, just that there is some sort of association. That's going to be our alternative hypothesis. So there's not going to be there aren't going to be equations and inequalities here. In the independence for two-way table case, our hypotheses are going to be statements, sentences. And so then we have to figure out what's our measurement going to be for determining whether or not we should reject the null hypothesis or not. And so what we can do for each cell in the table is compute this quantity, observed minus expected quantity squared divided by expected. So let's think about this. If there's not much difference, if the variables truly are independent of each other, then we shouldn't expect that much difference between observed and expected. So the numerator, I guess we're hoping, if the null hypothesis is correct, the numerator should be kind of small. And even in those cases where the difference is kind of big, as the difference gets bigger, the square gets bigger. If we had a large expected value to begin with, then we shouldn't count that against things too much, because we should expect greater deviations the more people that are involved in the survey. So if I have a higher expected count, I shouldn't expect, or I shouldn't penalize a difference between observed and expected as much. So if the null hypothesis is reasonable, then this quantity should be pretty small for each table, for each entry in the table, and therefore the sum of all these numbers should be relatively small as well. So the null hypothesis being true mean if the null hypothesis is reasonable, then we should expect the sum of these expressions to be kind of small. And so our statistic is going to be the sum of observed minus expected squared over expected for all entries in the table. We're going to call this statistic the chi-square statistic. So it's a Greek letter chi that we've got here. It's a capital chi. So when the null hypothesis is reasonable to believe, chi-squared shouldn't be too big. And so we're going to use a calculator in our studio to help us decide what the p-value is. But first we can compute all of those values, observed minus expected squared over expected. We can do that by hand. It's a bit tedious, but we can do it. But observe that the condition that we need to check in a situation like this is that no more than 20% of our cells, our table entries, should have an expected value less than 5. If we thumb back here to our expected values, we see that in this case, none of the expected values are less than 5. So that's certainly less than 20%. So we are good to go. So now we're just going to grind out those values. And I show the calculations on the next slide. Again, I would strongly encourage you to verify that these calculations are correct. In each case, there are 6 cells in my table. In each case, I'm computing observed value minus expected value. I'm squaring that difference, dividing by the expected value. And so I get these 6 values for each of my entries in the table. Then the chi-square statistic is going to be the sum of these 6 numbers. And so when I add them together, I get a number that's just a little bit under 4.5. And so the question is, how do I determine if that number is too big or not? So we're going to be using, as I said, we're going to be using a calculator, a probability calculator in our studio for a chi-square statistic. And so the first thing to look at maybe possibly is the diagram on page 238 of your text. You'll see what looks like what we call a chi-square distribution. It's unimodal, it's right skewed, it takes on values only 0 or bigger, and it often has a pretty long right tail. So we're going to see in T, I've got here's a question about T distributions, something about T distributions. T distributions are something that's going to be introduced in chapter 7. And so I'm getting a little bit of ahead of myself here, but there are going to be multiple chi-square distributions, each with a different number of degrees of freedom. And so we need to talk about what we mean by degrees of freedom. So DF is going to be our shorthand for degrees of freedom. The number of degrees of freedom in a two-way table is going to be the number of rows minus 1 times the number of columns minus 1. So in our example, we've got 2 rows, 1 for each gender, 3 columns, front, middle, and back. So the number of degrees of freedom is going to be 2 minus 1 times 3 minus 1. So that's 1 times 2, or 2. So I've got 2 degrees of freedom in this case. So let's talk about what I mean by a degree of freedom. So a degree of freedom in this scenario refers to if I'm giving you a two-way table with a fixed number of rows and columns, and I tell you all the rows and column totals, how many entries I can put in the table before I can fill the rest of it out. So in this case, I'm claiming that if I tell you only 2 numbers in the table, I can fill the rest of the table out if I tell you in advance what the row totals and column totals are. So you might want to go back and refer to the two-way table that we got out of XTabs here just to see this. But so my first column total is 41. So if I tell you that the first row, first column entry is 26, that automatically means that the first column's second row entry is 15 because they have to add up to 41. So the 26 was a free choice, but the 15 was automatically determined. If I move over to the second column now and fill in the first row with a 53, then because I know that there were 93 people who preferred the middle, that automatically determines the 40 below it. So the 53 was a second free choice, but it also determines the 15 next to it because I know that there were 93 females altogether, 94 females altogether. And so the 26 plus the 53 gives me 79. If there are 94 women altogether, that has to be means that the third column, first row, has to have a 15 in it. And that in turn determines the 22 below that because of the 37 people who prefer the back. So once I fill in the 26 and the 53, all the rest of the table can be filled in. It means that there were 2 free choices to fill out that table, given that I knew what the row totals and column totals were. So in general, once I fill out all row but 1, and if I fill out all entries but 1 in a row, that's the number of columns minus 1, and all the columns below that except for 1 entry, that's the number of rows minus 1, I can fill in all the rest of the entries. R minus 1 times C minus 1 is the number of degrees of freedom. Our R command that we use is P chi-square GC. What we do is we give it the value of the chi-square statistic, and the number of degrees of freedom. We'll include a graph as well. And the output of that is this part of a chi-square distribution, this right tail distribution. I can see that my p-value, my shaded region with 2 degrees of freedom, is a little under 0.11. What does this mean? If there's no relationship between gender and seed preference, then the probability of getting a chi-square statistic as big as the one we got or bigger is slightly under 11%. Since that's greater than 5%, we fail to reject the null hypothesis and say we don't have enough evidence from this table that males and females prefer where they sit in the classroom differently from one another. Okay, so a lot of labor. We had to compute the expected values. Once we had to get the row and column totals, we had to get the expected values. We had to compute the contributions to the chi-square statistic. And once we had the chi-square statistic, we could evaluate p chi-square GC to come up with a p-value. You might not be surprised to know that there is a one-stop shopping command. It's called chi-square test GC. It looks a lot like we've done with prop test GC or binom test GC. In this, with prop test GC, we gave tilde explanatory variable plus response variable, give it the data set, and then we just say graph equals true. It's going to do all the rest for us. Let's go ahead and execute this in RStudio. So if I put this in here, I get a lot of output. So first of all, we notice we get the two-way table, again, without the, basically gives us the result of X tabs. Then it computes the expected values. And then it computes all the contributions to the chi-square statistic. And then it gives us the value of the chi-square statistic. Slightly different for us because we rounded to 3 decimal places throughout. But then it computes the p-value, very, very similar, degrees of freedom. So it does all the work that we just did by hand. Very easy, very straightforward, and we get the same probability graph over here. So the reason why I'm asking us to do the handwork is to try to reinforce what it is that we're actually doing and not just rely on doing a few keystrokes to get the answer for us. So we love the chi-square test GC. It gives us this output, and it seems to match very well with our earlier computations. But again, I'm going to be asking us to do a lot of this work by hand in a couple of more examples. Let's do another example here in this slideshow. Let's look at the relationship between gender and belief in love at first sight. We talked about that a little bit earlier back in chapter 1. Now let's see if we can use a chi-square test to see if there's some sort of relationship among these two variables among Georgetown College students. Gender, again, is going to be an explanatory variable. Love at first sight, the response variable. I've rearranged the table a little bit to put yes first. And I've got my row and column totals. So once I've got my row and column totals, I can compute the expected values. I'll let you do that. You could stop the video for right now, work on this yourself for a little bit, and then compare with my computations on the next slide. Okay, I'm going to go on. Here are the expected values you should have gotten from your computations. And then once I've got my expected values and my actual values, I can compute the individual contributions to the chi-square statistic. We can proceed because all of our expected values are greater than 5. And here are those computations for both the females and the males. We add them up to get the chi-square statistic. This turns out to be a little bit more than 2 3/4. This time I have just 1 degree of freedom. If I know one of the numbers, I can fill in all the rest given the row and column totals. And so p chi-square GC with 2.769, 1 degree of freedom, gives me a p-value of 0.0961. If there is no relationship between belief in love at first sight and gender, the probability of getting a chi-square statistic this high or higher is just under 9%. And so we fail to reject the null hypothesis one more time, and we would say that we have no evidence of a relationship between these two variables. You could use chi-square test GC on this as well to compare. I would invite you to do that and see that it does confirm the work that we did earlier. Now I've got a practice question for you. Looking at the NHANES 18 data set, can we find a relationship between gender and income level reported? So I'm going to let you do that. In the slideshow, I've got a couple of slides with output from chi-square test GC, but I'm asking you to do all the work by hand in terms of computing the row totals and column totals, the expected values, and then the contributions to the chi-square statistic. And then you can use the chi-square probability calculator, p chi-square GC, to find out the p-value and make your decision. But you'll have slides with the output of chi-square test GC to compare that with as well. Good luck, and we'll be talking about this in class.